Welcome everyone. My name is Matteo Ferraresso, and I'm a PhD student in Matteo Bacca's lab at UBC in mechanical engineering. Today I'll be talking about the limits of cytoskeletal gel contraction. So some background about cytoskeletal gels. These are gels that have been made to study the cytoskeleton, but a simplified version of the cytoskeleton. So there's a chain backbone that, in this case, will be actin, that contracts because of molecular motors. So these molecular motors pinch will shorten the chains in the following way. So myosin pulls on the chains and contracts the chains, and this is driven by ATP hydrolysis. This causes solvent outflow and therefore contraction of the cytoskeletal gel. The objectives of the talk are to model the gel with a biphasic cross-linked polymer gel. And I will introduce a chain shortening model, which we've developed to specifically implement contraction from actomyosin to molecular motors. Then we investigate the energetics of gel contraction, specifically to look at spontaneity. This is because experiments have shown that certain networks contract and certain networks do not contract. And this is affected by both chain density, so how many chains are present in the network, and motor concentration. So how many molecular motors are present. So from literature, we find that there's a contractile region for such actin networks, and this is delineated by mainly three boundaries. So on the x-axis, we vary the cross-linker concentration, so how many of these cross-linkers there are. So a crosslink is where two chains join. And the more crosslink density, the higher crosslink density means the more chains we have in the network. Now on the y-axis, we vary the amount of motors. So down here, we don't have as many motors, whereas up here, there's a lot of molecular motors, so we get a larger contraction. And we see that there's three main boundaries. So the left bound delineates a minimum amount of chain density for contraction to occur. The right bound delineates a maximum number of chain density, whereas after that, no contractions occur. In reality, these contractions do occur. They are spontaneous, but they're just very slow. So they're considered not spontaneous. And then in the third region, the bottom bound, this is a minimum amount of motors for the network to contract. So no matter what chain density you're at, you need at least a minimum amount of motors for this network to actually contract and the cytoskeleton to contract. So with our model, we model the gel as with a thermodynamic free energy, and we model the contraction as chain shortening, so shortening of the chains. So everything is with respect to the dry gel, the reference state. This gel swells up to an equilibrated state, equilibrates with the environment, and from this point, the contraction occurs. We instantaneously inject energy into the system in the form of chain shortening, and we witness the contraction and get to this final contracted state. Now to recap that, at time 0, we have our swollen state with an initial free energy. This then, instantaneously, we shorten the chains, so we move out of equilibrium, and the chains contract. Since we're out of equilibrium, then we will get deswelling. But the difference in energy, in free energy between these two states is the instantaneous motor work. So the work that we have to put into the system for the contraction to occur. And then once we reach steady state, we reach a final free energy where we reach equilibrium again. And the difference between where we inject the energy to the final state, this determines, the difference in energies determines the energy during contraction. And this energy needs to be negative, so it needs to be dissipated, right? If we require additional energy to contract, then this process will not be energetically favorable and the network will not contract. So just a little bit about the model. We model the polymer chains with a free energy, that's Newhookian free energy. And then we model the mixing energy as Flory-Renner mixing energy. So this free energy is the elastic energy associated with the chains. And this energy here is the mixing energy associated with mixing the chains with the solvent. So this is dependent on the elastic free energy of the chains is dependent on the deformation of the chains, the microstructure, so how many chains there are, how they're cross-linked, and then temperature, which is constant in our case. And so the mixing energy depends on how much solvent we have, so how much swelling we have. And this swelling is determined by the swelling ratio, which is the ratio of final volume to initial volume. So a large swelling ratio means we're very swollen. A larger swelling ratio, a smaller swelling ratio means we are more contracted. So the elastic free energy has the following form, Newhookian strain energy, and we introduced this lambda m parameter, which represents chain shortening. So this is just the ratio of monomers in the normal chain to the contracted chain. So a smaller value of lambda m means a smaller chain. We then represent the mixing energy as Flory-Renner, and these two terms represent the entropic and enthalpic contributions to the free energy for mixing the solvent and the chains. And from this expression, we determine the stress and the chemical potential, which enables us to apply mechanical and chemical equilibrium to the system. So again, we're interested in this because we want to calculate the change in free energy between this initial state after we've shortened the chains to this final state and determine if this contraction energy is negative. If it's positive, it's not a dissipated term, and the contraction does not occur. So these are results from our model. So on the x-axis, we plot contraction. So we start from this point over here where we are at the ratio of volumes is 1. And just following the thin red line, we see that for some contractions, this change in energy during contraction is actually positive. So these contractions are not energetically favorable. We reach a certain point here where the contractions do begin to be favorable. So we see that small contractions are not favorable, larger contractions are energetically favorable. And these different lines represent different chain densities. So if we start with more chains, we see that this crossover actually changes. So this unfavorability region is dependent on how many chains we start with in the network. This is a different plot of this unfavorability region. So the red area is the unfavorability region. Outside, contractions are energetically favorable. Again, on the y-axis, we have our contraction. So this line delineates that crossover point from the previous slide where the x was located. And we see that this unfavorability region is affected by both initial chain density concentration, just like we saw in the previous plot. So those are different lines in this plot, but also initial swelling ratio. So Ji here is how swollen you are to begin with. So if you start from a very swollen gel, so you're up here, this unfavorability region actually disappears. And this is related to slack chains. When chains are slack over here in this region, because you're not as swollen, chains are more slack and loose, perturbing the energy doesn't have that big of an effect into the free energy. Whereas when you have chains that are really pulled and they're not slack anymore, perturbing the energy in those chains has this more significant effect, and you provide more energy for that contraction. So to compare with experimental results, again, the circles represent contractile regions, whereas the X's represent non-contractile regions. We can, with our model, we can accurately predict the third region. So this is the unfavorability region that determines that minimum amount of motor required to contract. So this is what the unfavorability region predicts. But if we also implement a maximum strain energy per chain constraint, we can also accurately predict, well, region 1, but also an upper bound, which was not specified in experiments. And this essentially represents crosslinkers breaking off. So if there's few chains and they have to take a large stretch, if they take on too much strain energy, these crosslinkers, the alpha actin molecules that bind different actin chains, actually split, and the network becomes not contractile. The third region, region number 2, is associated with slow contractions. So this is not predicted by our model because technically the contractions are spontaneous, but if we ran a transient analysis, we would see that these contractions are much, much slower because there's way more chains to contract with the same amount of molecular motors, which means not contractile if you look at it in a short time span of 60 minutes. So in conclusion, our model accurately predicts the boundaries of spontaneity for different cytoskeletal networks. And I thank you for your attention, and I'd be happy to answer.